Okay, cool. I think we can get started with maps and localization. So hello, everyone, again. For those of you joining us, my name is Andrei. I'm a research scientist at Waabi. And at Waabi, I work on a combination of both sensor simulation research as well as state estimation. And in this session, we will be focusing on the types of maps that we typically use in various components of autonomous driving. All right. So there are essentially two major categories of maps that we typically talk about. Namely, there are topological maps, and there are the traditional topological maps, and then these HD maps that you hear of quite frequently. And in this talk, we'll provide a bit of an overview of what these maps are, why they're useful for autonomous driving, and how to create them. So first, we will talk about these classic sparse topological maps. So these topological maps contain multiple different attributes, like the road topology, maybe the number of lanes on a road, on a street segment, and the direction of travel. And they're typically used in two major ways in autonomous driving. So they're used to get an understanding of the potential difficulty of an operational domain or a given geographical area. They might be used for tasks like business analysis to figure out, where it's beneficial to deploy a robo-taxi or autonomous trucking. And second, they're also used by the self-driving vehicles themselves, basically for high-level route planning. Basically, this thing can tell you how to get from point A to point B, just like a human would use something like Google Maps or Apple Maps or whatever to navigate from point A to point B in an unknown city. In terms of the data that you can use to assemble these maps, they can be produced from a wide range of data sources. So some approaches, and there's entire companies that work on this sort of stuff, for example, could be cameras that are mounted on dashboards. So aggregating this sort of data from dash cams because it's available at scale. Many drivers have them for insurance purposes, so you can crowdsource data for this purpose. You can also use aerial imagery from, for example, drones, from planes, from satellites, and so on. And of course, you can use your self-driving vehicles, whether it's cars or bipedal robots or trucks or whatever. If you can automate, if you can drive them through your environment ahead of time, you can capture this data and assemble it into maps. Now, as far as these topological maps go, in the industry, you have kind of three different approaches to build these maps. You have a more old school approach that is segmentation followed by heuristics. You have energy-based methods, and then you have fully neural network approaches. One of the most sort of classic ways to do this is segmentation followed by heuristics. And the idea here is essentially, for example, if you're interested in road segmentation, you might perform road pixel binary semantic segmentation on aerial imagery or satellite imagery or whatever. And then you would post-process this information somehow to obtain a road network. So maybe doing some sort of graph extraction. And in terms of strengths for these methods, you can just plug in a lot of state-of-the-art semantic segmentation methods that operate on pixels on top of these methods and then run the post-processing. But in terms of the weaknesses, the fact that you just plug in your semantic segmentation and then post-process it might mean that if there's some failures in segmentation, for example, due to partial occlusion or an unexpected angle in your satellite imagery, it will be difficult for the post-processing to recover. And of course, you're also dependent on whatever post-processing algorithm you designed, which might prove to be brittle. So rather than using segmentation that is followed by some sort of heuristic to get the road network, another family of work instead uses more principled approach, where you formulate the problem of road topology extraction as some sort of energy optimization task, possibly with neural network components. And the nice thing about this is that you can encode and optimize things in a structured manner, both semantically as well as geometrically. And in this example of paper, a method was developed that started with OpenStreetMap data, namely center lines, and then they were updated with precise road width information by doing inference in a Markov random field. So the idea here was that you would have an energy term using cues like the road segmentation mask, as well as image edges that you obtain from aerial imagery. And you would combine this with human-generated priors like the smoothness and consistency for the road boundaries, the road width. And This let you kind of have a joint optimization objective that had both sort of the neural network semantics as well as priors about the human encoded desirable characteristics of the map. And while mathematically this is more structured, these methods still rely on some handcrafted features and may fail to produce the fidelity and the precision that you require for tasks like automated driving. Now, a learning-based neural network approach for obtaining the road topology can help alleviate some of the limitations of these hybrid approaches. So in more recent papers, methods have used things like recurrent or graph neural networks to directly predict the road topology as a graph rather than having some sort of energy-based method where you use traditional semantic segmentation and some graph extraction. So for example, in this paper by Li et al., they use an RNN approach that iteratively produces the next vertex when you're drawing some sort of lane graph. And they can also use the same model, for example, for related tasks like building footprint estimation, like coming up with contours for buildings that you get in satellite imagery, which is very useful for remote sensing, for map building, stuff like that. And then another approach that we also have on this slide, follow-up work basically did something similar, but with graph neural networks to extract building footprints, which had the benefit that unlike the RNN, you could actually reason about the whole graph jointly, which meant that you no longer relied on a step-by-step inference process for the RNN, which made the network both easier to train as well as faster, just more efficient at inference time, which managed to approach some of these limitations of RNNs. And one cool thing about these graph learning methods is that these new methods are powerful enough to allow actually sampling from the distribution of maps. So we have here an example from a recent paper from NVIDIA called Neural Turtle Graphics, which lets you synthesize new and realistic road graphs from learned priors conditioned on the name of a city. So you can tell it to generate something that looks more like Manhattan or more like Paris, etc., and it will generate feasible maps. So this has applications in many parts of simulation, for example. I'm just going to show this again because it's pretty interesting. Now let's talk about the second category, which is HD maps. So HD maps contain both the detailed geometric information at a structured level, as well as semantics of the environment. And you typically use them for a wide range of tasks in autonomous driving. You use them for precise localization of the self-driving vehicle. You use them for providing additional prior knowledge for the autonomy system. And perhaps more importantly, you also use them for simulation. So often you will have a component of them that lets you do things like novel view synthesis or LiDAR simulation or stuff like that. So before we talk about the HD maps themselves in more detail, we should highlight the key properties. Oh, sorry. Anyway, we need to highlight the key properties that we want from these HD maps, right? So the most important things that we want from these HD maps is we want them to support very large scales, often encompassing entire cities, and to be globally consistent. And while in some applications you might have multiple passes over the same area that are required for building the maps, ideally we would like to reduce the number of passes through an environment before building these maps in order to reduce costs. We also want the ability to store the maps as efficiently as possible for ease of deployment and updates and so on. And we also want the maps to only contain the permanent elements of the world, so no dynamic traces that will interfere with other tasks like simulation and localization later on. So how do we actually build these HD maps? Well, building HD maps can be grouped into four big steps. So in the first steps, we want to select the operational domain in which we're interested and for which we want to build the maps. We then collect the data, and then we process this raw data to build the geometric maps that contain the 3D information. And then finally, we conduct some sort of labeling to add semantics to these HD maps using human annotations, AI models, or a combination thereof, like hybrid approaches. And depending on the application, we might then simply discard the 3D resulting geometry as a byproduct, or you also keep this, for example, if you want to do simulation. So let's begin by talking a little bit about how we built these geometric HD maps. So Once we have this data, the idea is that we want to split it into small chunks and fit trajectories to these individual chunks. And this is beneficial because it can be produced if it can be done in parallel. And then once you have these tiles that have been optimized, you can then align all of these trajectories in a joint optimization process, like some sort of large-scale postgraph optimization. And last but not least, you assemble these chunks and the raw data into a globally consistent map. So let's now briefly talk about simultaneous localization and mapping, or SLAM, and how it fits into this system. Okay. So SLAM is an important technology to jointly estimate the trajectory in the 3D map. And without going into the details, which could take up an entire graduate course, let alone a 30-minute tutorial, some of the main benefits of simultaneous localization and mapping is that it can be used to build large-scale, high-definition, high-resolution maps. It also enables navigation in completely unknown areas without any prior maps, because it localizes while also iteratively building and refining a map of that area. And another nice thing is that there are very robust, mature software solutions already available for multi-sensor SLAM that can be integrated into production systems. And of course, SLAM as its own field has a lot of applications beyond autonomous driving, for example, in augmented and virtual reality. We might also want to handle asynchronous sensors for a reconstruction system. So autonomous vehicles are often equipped with multiple cameras, which is necessary, for example, to cover the entire surrounding environment. And many existing multi-view SLAM systems often assume that multiple cameras also fire at the same time in each frame. But in practice, the multiple cameras that you have could be asynchronous with respect to each other due to technical limitations or by design. So, for example, the cameras might actually be synchronized with the spinning LiDAR so that they fire as the LiDAR kind of sweeps through the scene. And this is actually a common setup in many autonomous driving data sets. So to tackle this problem, there's papers like spline fusion and asynchronous multi-view SLAM, which formulate a more generic SLAM framework, where you no longer model the frames as individual poses, but rather have a continuous time parametrization for your trajectory. And then you optimize this spline-based or Gaussian process-based or whatever trajectory parametrization instead. And this lets you asynchronously fuse different modalities, not just multiple cameras, but cameras and radars and LiDARs and inertial measurement units, etc. And of course, not everything should be in the map. Dynamic objects should typically be removed. So you typically run a semantic segmentation or at least some sort of object detection offboard on the geometric data you assemble to remove this sort of stuff before you build the final maps. So now let's talk a little bit about how you actually generate the semantic elements of these maps. On top of the geometry, like I mentioned earlier, HD maps contain a lot of different kinds of rich semantic information, like the precise locations of lanes and road boundaries, things like crosswalks, intersections, as well as potentially more abstract information like traffic light to lane associations or whatever the rest of the system might need in some cases. But of course, there are some challenges to adding this kind of information to HD maps. So first, the maps change all the time due to, for example, construction. You need to keep expanding your operational domain and so on. It's also common to require multiple passes through the same area in order to build these accurate, dense geometric representations, for example, because of occluders. And last but not least, relying on human annotators to hand label the location and attributes of all of these semantic elements can be very labor intensive and cost a lot of money. So what we actually want is a way to infer this information in a manner that is fast, that is robust, and that is as automated as possible in order to get all of these, in order to overcome all of these challenges. So one cool thing about this is that we can actually combine humans and robots in this inference process, and humans are still left in the inference loop because they are required because of the fidelity requirements necessary for these HD maps, namely at the centimeter level of precision. So typically speaking, the centimeter level precision that we're interested in is often beyond the current capabilities of machine vision alone. And generally speaking, in order to reduce these costs, we want approaches where machines and humans can collaborate to actually minimize the total number of dollars spent to build a map. And in the next few slides, we will showcase some works that can generate various components of these HD maps in a way which is amenable to human-in-the-loop workflows. So let's start with road boundaries, as we see here. Knowing where the road boundaries are, that is delineating the separation of the drivable surface of the road and the sidewalks, is a crucial aspect for safety and navigation. And the industry baseline is typically to have human annotators draw these boundaries from scratch as part of the HD map production process. But as we highlighted earlier, this can be a very expensive task because we need to annotate entire cities and potentially keep updating these maps, so this is not scalable. And in addition to this initial human annotation process, there's also a need for multiple quality assurance rounds to make sure that the polylines are correct and precise and there's no mistakes. So the question is, can we automate this process so that human labelers only need to do the quality assurance process and quickly and easily adjust incorrect predictions rather than annotating everything from scratch? So in order to tackle this, we need model outputs that are easily editable for humans. So this is why we are very interested in directly outputting polygons or graph structures in general from mapping models rather than pixels, because this matches the final representation that we want to encode the maps under. And it's also easier for the humans to adjust than the raw pixels. Humans can very easily have an interface where they can quickly delete a map vertex or move it around if a model makes a mistake, which is much more efficient than drawing everything from scratch. Okay. So in the previous section, we saw a few methods for computing road networks and their boundaries. And now we want to estimate something that is even more fine-grained. We want to estimate the boundaries of all the lanes, not just the road or not just the center line. So this problem can essentially be formulated as discovery first, and then inference in a directed acyclic graphical model, or a DAG, where here the nodes essentially correspond to geometric and topological attributes. So more specifically, given a temporally aggregated point cloud that is projected in a bird's eye view BEV image, we aim to find the best DAG that could describe this road network. Now, the space of possible graphs is, of course, gigantic. So the idea here is to do some greedy methods to instead greedily construct a graph and then use basically a neural network to predict iteratively what the next node of this graph and its topological properties are. So to make this a bit more clear, we can look at the steps of this inference process on the top. So in the first box on the top, we can assume that we already have the inferred DAG that you see at the current timestamp. And then in the second one, we find the direction where we expect the next vertex. And this is highlighted by the yellow box. And then we infer the position of this vertex within this RY and then predict its state. So in this case, we find the coordinate of the vertex that we want, that a human would draw, and then we predict correctly that it is a fork. So the idea is that at this fork, we now continue drawing, as you can see in the image below. And once we finish the current polyline, we remember that we had this fork, and then we go back to it and then essentially do this whole process until we run out of sort of graph nodes to process. Kind of in we just grow this tree until we are done with every single branch. And in this video, we can showcase that a model like this can draw boundaries incrementally on road imagery. And it does so kind of like a human. And it can deal with a lot of complex lane topologies, so not just boring straight highway roads, but also forks, merges, and intersections. And in slightly similar, but a little different still direction, instead of lane boundaries, other lines of work aim to extract the graph of lane segment center lines instead. For example, centerline det creates a global map of centerlines by first predicting the lane centerline segmentation masks, and then using transformers to iteratively predict the vertices of the centerlines, one vertex at a time. And of course, some of these models and the citations that will be easier to see in the recording are just a few examples, because this field is very, very big and it's constantly evolving. So there's constantly new papers that come out that improve the techniques over the previous ones. Okay, so let's now switch gears a little bit away from building these maps offline and look at ways to do mapping online instead. Now, online mapping is a must for safety because maps are, of course, not always up to date, and localization can fail, or we might not have maps at all to begin with. And mapping every area can be expensive, And updating it every time there's a change can also be extremely expensive and difficult to scale. So in some of these cases, it's important to be able to produce the map online as you're driving through an area that you recognize is currently unsupported. Construction alone can change the world in a huge number of ways, as we can see in these pictures where construction might close a road off completely, it might close off a lane, it might move a lane, and do another 1 million different things to change the way you have to drive. And of course, online mapping comes with its own set of challenges on top of traditional offline mapping. Namely, occlusion is a big concern because mapping elements can often be occluded by objects in the scene like vehicles and pedestrians. But of course, unlike offline mapping, here we have much less information to work with. Online mapping, of course, can only detect elements that are within the range of your onboard sensors. Again, you don't have the luxury of aggregating hours and hours of data and chunking it very nicely, so you always have very dense data. Of course, construction elements and construction vehicles can alter how the map is interpreted, so where the lanes should actually go. So figuring out where all of these elements are and making sure you don't miss them is also very important. And of course, for autonomous driving, it's important that the software runs efficiently because now you're no longer running your mapping software off-board in some cluster. It's actually running as a node as part of your robotic system. So it must be able to run in real time or very close to real time to react to these changes. And of course, last but not least, you have to be able to create consistent maps over time as you're driving, which is very challenging because, again, you don't have the luxury of waiting until you have all the data and processing it nicely at once. You have to be able to process this as you're getting observations incrementally. So one way to tackle this earlier on was to do 2D lane detection. So detecting the lanes in the camera image. This is like a classic example of a task that you do in autonomous driving. So these approaches typically use some sort of deep learning to segment the lane boundary pixels in 2D and then clustering them into individual lanes and then fitting some sort of primitive to a lane, maybe like a spline. And it's important to point out here that doing precise lane detection in 2D does not necessarily mean that these lanes will look good or make a lot of sense in 3D, which is actually the space that we're interested in driving in and planning in. So an example in the image here is that we can show that we predict the probability of a lane boundary in 2D and cluster it in 2D. That's what the color coding means. And then we reproject these probabilities into an overhead view, right? The reprojection is the third image. And for comparison, you also see the sort of unprojected camera image as well. And you can see that although the lane detections look very good in the camera image, the probability output actually becomes pretty diffuse as the image as the distance increases. And then these detected lane boundaries conversely also become less accurate in 3D. They become kind of blurry and wide as you move farther away from the position of the camera, even though the physical distance isn't that long. It's like maybe, I don't know, 50 or 100 meters. So instead, the idea is to reason about the lane structure directly in 3D, because that's the space that we are interested in planning. And actually, as we will see, a lot of the modern approaches to do this, whether it's camera and LiDAR, single camera, multi-camera, the modern methods pretty much all do it like this for this reason. So like I mentioned, there's a ton of papers that approach this. One example being, for example, 3D lane net, which applies inverse perspective transformations, to deep features, starting with a single image and then predicts center lines and lane boundaries directly in 3D. Of course, it's beneficial to be able to process multiple cameras at once. Spoilers. So in the context of online mapping, you can definitely and should use multiple cameras as well. And in this example, we're looking at the paper called Lift, Splat, Shoot, also from NVIDIA, where camera imagery from multiple views is fused to predict the top-down bird's eye view segmentation of all mapping elements. And the idea being that in the first stage of the model, each image is kind of lifted from its local image feature plane that is two-dimensional into a 3D frame that is shared across all the cameras. And this is done kind of in a soft way because you don't have explicit depth information. And then in the splatting stage, essentially, you fuse all of these uncertain features using a point pillars architecture to convert them essentially into this top-down bird's eye view segmentation that includes the lanes, drivable areas, and other stuff you might be interested in when doing driving. And this means that you can produce outputs like this, which look pretty good, and they jointly reason about the map itself as well as about the dynamic objects that you see in the environment. And it processes 6 cameras at the same time. Okay, then you have HDMapNet that similarly maps this deep perspective features from surround cameras through an MLP into a bird's eye view. And then you fuse them with deep LiDAR features. So now you're also adding LiDAR to also output a semantic segmentation map, instance embedding, and a direction map. And then you post-process these features into vectorized outputs for lane and road boundaries, crosswalks, that sort of stuff. So you have the network output some intermediate outputs that are then post-processed into vectorized ones. And the results look pretty good in practice, where the method, again, can reason about where the curbs are online, where the lane lines, et cetera, are, as well as potentially dynamic objects, as you'll see in the intersections. Actually, no, I think that might be, I think it doesn't, yeah, it only does the map elements, and the rest is just what you see in the LiDAR. So you'd need this in addition to a perception system. And the nice thing about this is that you can also accumulate these single frame predictions now that you have them consistent, and fuse them temporally in order to create pretty large scale maps all online. Another recent paper is a line of work which goes one step further. And here you train a network to actually directly extract structured vector graphs from the online camera data alone. So you're no longer reliant in these approaches on a custom post-processing algorithm. Yeah, and then Map Tracker as well. This is yet another paper that produces really nice, consistent results, all in real time and all in a way which can be aggregated over time. And the nice thing about these maps, again, is that they are topological. It basically outputs graphs. Sorry about that. It basically outputs graphs, which can then be very effectively both stored as well as used in downstream tasks like your planner or your perception system, et cetera. And of course, mapping is just a means to an end, right? You'd like to learn representations that are ideally optimal for the task of driving. And here, MP3 is an end-to-end network which tackles this very task. And the name, which you've probably also seen in the perception section, it stands for mapping, perceiving, predicting, and planning. And the idea here is that it is able to integrate an online mapping component to jointly do this together with prediction and perception and plan accordingly to run successfully in closed loop. And it can do this without any reliance on prior maps. So to summarize, we discussed these two big categories of maps that can be used in self-driving, namely topological maps and HD maps, and showcased how to build them using algorithms where humans and machines can collaborate effectively in order to reduce the total cost. Finally, we also looked at several approaches for online mapping and how they can be used to reduce the reliance on existing maps. And with this, we reached the end of the mapping section. The next one will be the localization one, where we will look about how to actually figure out the position of the vehicle into a pre-built maps, which is actually necessary in order to allow autonomy to leverage the information that is stored in the map. So we have a few minutes for more questions, and then we can continue. Thank you. All right. Any questions? There's no questions on online. Any questions here? Yes.
So in the beginning of this presentation, you mentioned collecting camera data from a bunch of different cameras, sources, right? So do you use all that data to then stitch up a map, like a 3D map, or is that how it works?
Yeah, that's a very good question. So there's some information. I think there's companies that do this. I don't have a lot of details, but there's multiple ways in which you can crowdsource this kind of data. So you can collect the raw data and then run structure from motion or some sort of system like this, maybe combined with GPS tracks in order to build the map models like that. Although in that case, privacy is an important concern because depending on where you're collecting this data from and user preference, you might not be able, or you shouldn't just directly stream absolutely everything from the dash cam. It might not be legally allowed. One way to tackle this, I've seen where I think some automakers, what they do is they actually they basically do online mapping, and then they upload this output. Like, for example, those vectorized outputs that you saw, only that gets uploaded with GPS tracks and everything. So that basically, because you're only extracting lane lines and whatever, personally identifiable information is just completely excluded by design. So then you get these chunks of vectorized maps from your fleet or whatever, your cars, as they're driving to an environment, and then you can aggregate this data on the cloud and then redistribute it once you kind of filter it so it's nice and consistent. And this can let you, because it's vectorized, it can actually let you do things very efficiently and do over-the-air updates.
So you're mostly responsible for collecting the crowdsourced data. Is that it? Or do you do anything?
Yeah, I'm not sure. I think I've seen some papers from some OEMs. I'm not entirely sure. I remember. Might have been Daimler, but don't quote me on that one, where they talked about a system like this. I don't know exactly what kind of post-processing they do, but that's the idea. You have these lightweight semantic elements that get uploaded, and then you still need to align the information from the various sources that you get and kind of filter out noise and all that stuff. And then once you post-process it, you clean it up. Maybe you have human QA, and then you update the maps that are in your fleet. That's one way to do it. Right.
You mentioned privacy. What's your strategy at Waabi around clinics, military bases where you're not supposed to collect data?
I can't give any specifics because I'm not an expert. I don't know, but there are people who are in charge of things like safety and certification and operations and all the legal permits. So they are the ones who are in charge of sorting this out. But yes, I agree. This is, there's like entire positions at companies like Waabi and related that are only tasked with this because it's something where a special care needs to be taken. Of course, there's special permits you need to get when you're testing vehicles, even with a driver behind the wheel. So there are very talented people that are much smarter than I am that are taking good care of this sort of stuff. I don't know that much about the regulations. Okay, one more question.
We mentioned all the images, cameras, and also mentioned LiDARs. Are there anything else?
Yeah. Yeah, I mean, indirectly, you probably also use GPS and GNSS trajectories for the localization aspect, as we will see in the next slide deck. You can also build maps with radar. They have the advantage of they're a little trickier to build and to remove the noise before you accumulate the data. But then you have the benefit of basically having maps that are kind of by design more resilient to weather conditions and just fog and stuff like this that you can then localize to. But it's also a function of whether, if you want to do human annotation and human QA, and you're interested in validating that your lane lines make sense and stuff, it's more difficult for humans to validate like radar data, like lane lines and stuff aren't really visible, whereas LiDAR intensity and cameras are more straightforward to validate by experts.
Right. The sense how much money sensor will cost, such sensors will end up being on such connectivity.
Yeah, and of course you can also do it cross-modally. So there are some papers that build maps with LiDAR and then use cameras or more inexpensive radars to match against the fancy LiDAR maps as well. So you can potentially have like a mapping fleet with more expensive sensors, and then the production line cars that you might sell with assisted driving or whatever, they're using more inexpensive sensors, but still leverage these HD maps. Yeah, of course.
Sensor end up building more accurate. Something like LiDAR is barely use visible is barely. You need to use both.
Yeah, that's a very good question. So the question was, which sensor leads to the most accurate maps? I think it's more a question of shifting computation almost. So I think you can build really, really accurate maps with all sorts of sensors, including relatively low-end cameras. It's just that you need to do more work, more heavy lifting algorithmically, and spend more time, for example, maybe training a foundation model to learn meaningful depth priors and stuff like this. Whereas with the LiDAR, as long as you have the initial calibration, you can kind of just drive around and run an off-the-shelf LiDAR slam on it, and you'll have like a really nice map typically. But of course, then you're basically, your algorithmic costs are lower, but then your sensing costs are higher. So it's about finding the right balance. Okay, cool. So let's move towards the final session, which is localization.